I will start describing what my talk will be about today. So I'll talk very generically about the next generation of CSP from my views and from what I can see it's happening in Europe. And I describe then mainly two things, hybridization with PV and supercritical CO2 cycles. And like I said, well, Hishan introduced me already, and I'll represent KTH. I'll start briefly talking about KTH. So KTH is a university in Sweden. It's one of the oldest universities, founded in 1827, and it's the largest technical university here in Sweden. We are approximately 14,000 students, some 4,000 employees, here including the PhDs. And often we are ranked top 30 globally in engineering fields like mechanical and electrical engineering mainly. And here is the background is just a picture of our university and the main campus. In KTH, being a large institute, then it's split in several schools. The school that I work at is the Industrial Engineering and Management, which is then divided into several departments. And in that regards, the department that I work at, it's the Department of Energy Technology, which is also split in three larger divisions. Energy Systems, which is looking more at the overarching electrification issues or land and water connection at the country level. The Applied Thermodynamics and Refrigeration, which is looking more from the consumer side and end user demand. And the Heat and Power Division, which is the one that I work, and we deal more with with the generation side. And within the division, we are approximately 40, including half of them senior researchers and half with PhDs. And we have 6 major areas we focus our research on. So you could see it split it in power to X, or bioenergy and thermochemical conversion, centralized renewable energy systems, distributed energy resources, polygeneration, thermal processes, and turbomachinery. I won't introduce myself since Hishan already did extensively. So I'll say, besides that, I mean, I lead research in the areas like Hishan mentioned, and all the areas I mentioned before, but particularly mainly 2 projects connected to this. So the SOLARSCO2OL, what I'll be talking about, which we deal with CSP and supercritical CO2. Well, the Flex and Confu, which is power to X. And in the past, my experience has been in the field. I mean, like Hishan mentioned, in solar reserve. And I've also had a period, 4-month period in Madsen earlier, as well as Total for a bit less than a year, working in the same field. So I figured out that I was the first speaker, and I wanted to start very broad to end up very narrow to what we do in the SOLARSCO2OL project. So I'll give this slide, which is very generic, but gives us a bit of context. I just wanted to highlight from this to put into picture that the potential from solar energy is so large that not only when you compare it to other renewables, which are here on the left, but also compared to our needs, it's roughly 3,000 times the total global energy needs that we have, and that including heat, electrification, transportation. So not only electrification. Now, when it comes to harnessing solar energy to produce electricity, we have today 2 major commercially deployed technologies, right? So one is CSP, like you see on the top, and I'll be talking about that, and the other solar photovoltaics or solar PV. So we'll be focused today on solar CSP, and to be clear, since I figure also the audience is very generic, many are students, the basics of CSP are depicted here using, as an example, one of the plants from Torresol. But in principle, what I want to keep in mind or highlight is that in a CSP plant, 2 major processes happen. So one is we harness solar energy to produce high temperature heat by means of concentration. And then this high temperature heat, it's used to produce electricity by means of a conventional power block or thermal power unit. Now, the fact that we have high temperature heat as an intermediate step, it's actually one of the main advantages of CSP. And that is because we can integrate cost-effective thermal energy storage at larger scales, like Hishan mentioned. Or also, we can hybridize with other means of thermal power generation. In the picture, you see just an example of what, I mean, the same schematics, but what that means. So you have the sun, which irradiates on the heliostats, which reflect the light on top of a tower where there is a heat exchanger called the receiver. Through this heat exchanger, we're getting a fluid. In this case, is molten salts, which are initially cold, but then they get hot after being exposed to the light. And then they are stored once hot and they can be withdrawn from this storage tank to produce steam to drive a power block and produce electricity upon demand. So that is the advantage of CSP. This example considers a tower technology, but it's not the only one, and actually the most commercial one, and you'll probably hear more about it later. It's a parabolic troughs, and there are other less deployed, but also commercial, like the linear Fresnel technology or the parabolic dish. Now, having said, introduce a bit about what is CSP, I also want to highlight that both CSP and PV are cost effective today, and we need to understand the value that each one brings. So first, I'll just refer to the picture on the left. So on the left, you can see that both technologies have dramatically reduced cost in the last decade, with a steep decrease in cost from photovoltaics, but also seen from CSP, even though there are way less projects being deployed. So in regions where we have good irradiance, both technologies can be competitive. And furthermore, they can complement. We have seen, and recently, very competitive bids for PV, but we have also seen very competitive bids from CSP when they incorporate long duration storage. And the fact that they can incorporate storage is the value of CSP. And therefore, that's why we can hybridize them as an opportunity. And I want to highlight again that this is a steep decline in cost that you can see from both. PV has reached this decrease in cost after more than 200 gigawatts installed capacity globally. Whereas for CSP, we have roughly 6 to 6.5 gigawatts capacity installed, so there's a big room for improvement. Where is the room for improvement? So I think here I wanted to highlight some of the challenges or opportunities that CSP brings along. So CSP, it's clear that, as I mentioned before, that one of the main values is the storage, but it also offers, and Masen knows very well, several macroeconomic values, for instance, job creation or local content, because of the magnitude of the projects. However, this magnitude of projects, means that CSP today requires being deployed at large scales to be cost effective, and that's a conflict because larger, projects demand large investments, which makes them harder to reach financial closure or to be financed. But at the same time, it's an opportunity. From an R&D point of view, we're investigating solutions that could be cost effective also at smaller scales so that we can deploy them easily. Still, with these 6 gigawatts installed today, you can see from the plants in Spain, for instance, where no further deployments have been seen since 2011. Every year in Spain, the CSP capacity or generated energy increases, which means that we are learning, or the community is learning, from operational maintenance techniques to keep improving it. And we've also seen projects being deployed elsewhere besides Spain, which was the initial renaissance. And projects are becoming more bankable. We'll hear more about projects later, especially from Morocco and Master later. The bankable projects, though, are mainly using what's so-called conventional technology, so using traditional oil or molten salts. And a trend today, then, to increase this competitiveness, to move from the state-of-the-art, is to hybridize with PV, as we will hear. And also, from an R&D point of view, what concerns CSP, it's to shift to technologies that allow us to reach a higher temperature and therefore higher efficiency. However, this is still at a low technical readiness level. So let's say it's not fully commercial, and it's only at R&D level. What is happening in EU? So from the European perspective, Europe's set what we call the strategic plan for CSP 2017, or in the steering committee, there were agreed 12 research and innovation activities that were set as a priority on how Europe sees CSP, advancing state of the art. Among this, so here you have just a few, one line for each, but we have linear Fresnels, next generation, so using molten salts, or next generation of troughs using molten salts, enhancing the silicon oil using parabolic trough, moving to solar towers with air receivers, advancing the state of the art of molten salt solar towers, since there are only few deployed commercially, moving to a next generation of tower plants, here meaning any type of concentrator side or a heliostat design, pressurized air cycles, multi-tower beam down systems. Particularly, I want to focus on the last 4 because that's what I will be talking later, but thermal energy storage, supercritical cycles, improving flexibility, and combining air and supercritical CO2 cycles. And what you see in the bottom, it's just a number of projects funded by the European Commission that are still ongoing, addressing these issues in one way or another. So I'll talk then about supercritical CO2 and CSP as one of the trends I mentioned earlier, and why is that a trend, or why do we see an opportunity there? I highlight 3 things. One is that we can enhance the efficiency of the system because they allow us to, or these power blocks can operate at a higher temperature than steam cycles, which are the state of the art. At the same time, if you look at the picture in the center, which is a schematic from Ecogen, but it gives you perspective at then how one power block of a supercritical CO2 cycle is roughly a 1/5 of volume than an equivalent size steam power turbine, or even more. And this is because it's a 10 megawatt. If you go to 100 megawatt, the difference could be even a 10th in volume. And at the same time, as I was mentioned earlier, because of this compactness, systems based on supercritical CO2 can bring an opportunity in the way of, maybe we can have systems or CSP plants that are at smaller scales already commercially attractive from a price point of view. The US, in that regards, then set a very strategic and plan to reach what they call the Generation 3 CSP, which is around designing new systems that will allow us to harness or deploy, this high-efficient supercritical CO2 cycle. They highlighted 3 paths, so different technologies that can lead the way to do that, using liquids as a heat transfer fluid, and that's the molten salt path, or using solids in the fluid as well, that's the falling particle, or just the gas phase, which is using air. And what you see in the example here on the right, it's more the typical layouts or representative layouts of the one being investigated. So one from the liquid path, which is using sodium and chloride salts as storage, and one from the air or gas phase, which is using an indirect air for a supercritical CO2 cycle. However, what we say, or from investigations, here in my team or in Europe, a one step before getting there, before moving into new technologies, it's to deploy our mature technologies the most we can and introduce this cycle. Because already at the temperatures of 580 degrees, which is the conventional molten salt temperatures, this cycle can offer a myriad advantages. And you can see one here, just from the graph on the bottom. Even at its simple configuration, we can reach efficiencies that are approximately the same as steam cycles. And if you, increase the complexity of the cycle, adding recompression or so on, you can even go further in efficiency. So there are advantages that can be seen already at this temperature, and therefore we see an opportunity of already installing systems, with molten salts, but also using supercritical CO2 cycles. Then when it comes to Europe, so what is Europe doing in this regard, so in CSP and supercritical CO2 cycles? We have a number of industries, as you will hear later, that are interested in the field, or that are prominent equipment manufacturers deploying or trying to deploy and develop compressors, turbines, and so on for this system. There is, as we heard earlier, already demonstration plants are happening in the US and in China when it comes to molten salt plus supercritical CO2 cycle. And already I mentioned also that in the set plan from the EU, so in the strategic plan for CSP, there is acknowledged that we should look into these new supercritical cycles. But today, if you look at until very recently, most of the projects that the European Commission had funded were at a lower readiness level. With most of these targets of development was just reaching lab verification tests, but not a real integrated cycle demonstration. And here are just some of the few projects that started some years ago, like the supercritical CO2 Flex or the supercritical CO2 Hero or Scarabaeus. We have, though, in Europe, and I'd say mainly in Spain and Germany, but gained a lot of know-how in CSP and molten salts. And therefore, we have a good platform to actually lead this demonstration of supercritical CO2 cycles with CSP. Besides this, like I mentioned, another key aspect is that we want to highlight from R&D in Europe. It's the hybridization with PV, and as we will hear further, not only hybridizing by co-locating with PV, but active hybridizing by using molten salt electric heaters so that we can harness excess electricity from PV. With that in context, then we started a project a month ago. The project was granted some few months ago, but the project kicked off last October, which is called the SOLARSCO2OL project. The SOLARSCO2OL project, it's a demonstration project that aims to demonstrate in Europe for the first time an integrated megawatt scale supercritical CO2 cycle that is running from molten salts as the conventional salts at the conventional temperature seen in other plants. The demonstration will happen in a facility in south of Spain, in an existing CSP plant. And to do this, we will also, besides demonstrating the components of the cycle, running from a primary heater with salts, we will also demonstrate a megawatt scale molten salt electric heater, which will be optimized for this purpose. The project, it's composed of the consortium. We are 15 partners, all European, but one, which is Morocco. So with our partner from Morocco, it's Molten. The consortium, it's very industrial driven. 10 out of the 15 partners are industry. You see some here. So Abengoa, Lointec, Mactel, Franco Tosi, Baker Hughes. They're all prominent industrial partners, or from Europe in the field of power generation and CSP. We have associations, so Stella, the Solar Thermal Energy Association, or in Europe, and research centers that support the R&D aspects and development of the components and system integration issues, including us. The project is coordinated by Brina Consulting, and the scientific coordination is led by us at KTH. And it would go for 4 years, so we expect to have our the installation by around 2022, by end of 2022, and have it or start installation then, and have some data already by 2023. If you look into perspective, is what I was mentioning. So the first 2 years, we will focus a lot on the actual development of components. So it's more at the facilities of the suppliers, understanding or validating the respective heat exchangers, the compressors, the turbines. And then in the last 2 years, just moving into the demonstration phase in south of Spain. Beyond the project, of course, we expect that the experiences learned from the design and installation, and integration, and the data, of these components integrated, allows to understand how to scale it up for larger systems, so that all the suppliers involved can adopt it as a commercial product, and also that the industrial partners involved or potential off-takers like Molten or Abengoa, which develop plans, then also be able to replicate this in other concepts, in other power plants in the future. We investigate many layouts, but one layout that we see could be interesting among others, it's the one shown here, which will be one of our replication layouts using NUR3 as a base from Morocco. And it's just a layout where you see in the bottom a conventional molten salt tower, but we hybridize or integrate with PV actively by having a parallel electric heater that allows to use some excess PV when needed, or excess electricity from the grid when needed, to also store energy in the tank if needed. At the same time, the fact that you have this heater allows the plant overall to be more flexible behind the meter. And all of these components, being the PV, the electric heater capacity, or the rate capacity of the CSP plant, can be adaptable to any design needed or from the market. And what is interesting here is that we're not suggesting any drastic change on the CSP technology itself. This is exactly how NUR3 relies. So it's a molten salt tower plant with tanks. But we are innovating on the supercritical CO2 cycle and the electric heater. Talking about electric heaters, just wanted to have one slide about it because they seem to be, rather mature component. We have used electric heaters for many other applications, but in fact, the molten salt electric heaters themselves, they have not been deployed commercially, or they are not an off-the-shelf product. So one of the other research we do at KTH, together in collaboration with Exit, which is a company in the UK, which is partnered with us, it's working in optimization of these heaters through an industrial PhD project that we have set up. These heaters can be used in layouts like the one I shown earlier for CSP, but also for so-called Carnot batteries. And Xheat, through their subsidiary Seiko, will demonstrate in the SOLARSCO2OL project a 5 megawatt, or actually 6 megawatt electric heater. There are different phenomena that are considered when designing these heaters. That's why they're not an off-the-shelf product. Because of the relationship of the fluid that we're dealing with and the design of the baffle of the elements for heating or the resistances. Well, some of the main challenges are listed here. So you have solidification in inactive, so the salts themselves, overheating of some parts of the heater itself. So here, I just mentioned in the terminal box, if they're not production, the design of the insulation. Of course, you want to, this is a heat exchanger at the end. So controlling pressure drops, controlling also that the element surface temperature does not exceed at certain parts or creates hotspots so that they will degrade the salts. So there are a number of design aspects that are relevant and not obvious to consider, especially when scaling up all of this system.
Rafael?
So that's part of the research. Yep.
2 minutes, please. Thank you.
Last slide, so perfect. So I just want to end then saying, from the talk today, I wanted to keep some key takeaways. So one is, solar electricity is cost effective. And with that, I mean, not only PV, but also CSP. And we need to understand that the value of CSP lies on the opportunity to offer storage. There are many opportunities for enhancing cost competitiveness of CSP further. I mentioned some, like hybridizing with PV or shifting to supercritical CO2 cycles. And supercritical CO2 cycles can bring an opportunity, but still to operate them at 700 degrees Celsius are yet to be proven because of the needed advancements on the CSP side technology. Therefore, that's why in the project we started, the SOLARSCO2OL, we believe that's a step towards that direction, but using bankable or already existing molten salt technology, we wish to demonstrate megawatt scale components of such technologies, so turbine compressor, heat exchangers, and the molten salt electric heater. And like I said, it's an industry-driven consortium that will go for years, and hopefully you hear more from us. So thank you. And here, my email if you have any other question.